Okay, thank you. So first, I want to thank the organizers for allowing me to give these 2 additional lectures. Very nice. And just, yes, first thing, since I'll try to make everything accessible to a broad audience, but please, if something is not clear, do not hesitate to ask questions. Yeah, so that's important. So what I will talk about today is Hormander's theorem. And today I will talk about Hormander's theorem and its extension with the help of rough paths to rough differential equations. So first, let me recall what is the classical Hormander's theorem. So we, let's say we work on our Euclidean space. So we have a certain number of V vector field, D smooth vector field, on R E. Smooth, I mean smooth with bounded derivatives of all orders. And then we look at the stochastic differential equations. dyt is equal to, well, basically driven by these vector fields. Yt along Brownian motion. So here it's a d-dimensional Brownian motion. Sum for I equal 1 to D. Okay, and what Hormander's theorem? Oh no, wait. And of course, you need to make one assumption on the vector, some assumption on the vector field, and so you start at certain position y or y0, let's call it. And what Hormander's theorem tells you is that if the Lie algebra generated by this vector field it's at the point y0, it spans the whole tangent space. Then, for any fixed positive time, the random variable yt, it has a density with respect to Lebesgue measure. With respect to Lebesgue measure on RE. So that is the classical Hormander's theorem. So the geometric intuition is quite clear. It's quite, I mean, I will explain just a little bit now why it's very natural to have this Lie bracket condition. So first remark is that, let's say this, okay, so first remark is that we have this condition at the point y0, but it's it really means that if it's true at the point y0, it's also true in a neighborhood of y0. So it's not exactly a punctual condition. It's really more on an open set. Okay, and so to get a bit of an intuition, so first thing is that what happens in case this does not hold. So if we had that, let's say in the whole space, everywhere, or in the neighborhood of y0, it does not matter. If it had a dimension of this, if this L, okay, let me call L, this Lie algebra. If this was, let's say, equal to another number f, strictly smaller than E everywhere, then what happens? Well, you know that, let's say you look at this point y0 in your space RE, then basically because of this, you can at least locally around y0, you can have a strict submanifold M such that basically just its tangent space is given by the Lie algebra at each point. Okay, so it's a classical result. And so what does that tell you? In particular, of course, this one here, it contains all the brackets of the vector field, but that means that in particular it contains all the vector fields. So if you look here, not Brownian motion, but just any classical ODE, so if you look at any classical ODE y dot driven along this vector field, say beta for a smooth path, then if you start at y0, it will stay in this manifold, okay? It has to stay in M. So in particular, okay, so I mean, at least for a short time, let's say, you would have the same thing for these differential equations. You would stay in this manifold. And what does it mean to have a density with respect to Lebesgue measure? It means that if you look at any fixed subset of your whole space, which has 0 Lebesgue measure, then with 0, you almost the path which which stay in this set, or let's say which was the terminal value here is in this set, it has probability 0. But here, it's clear that with positive probability, you will stay in this set. And so, I mean, the Lebesgue measure of M, clearly, since it has strictly smaller dimension, it is 0. Okay? So at least this is, of course, this is the other direction, but this shows at least why this is quite natural to have, that if this condition would not hold, then you certainly don't expect something like this to be true. And in the other direction, if, on the other hand, at any point, the vector fields, the Lie algebra spans the whole space, then that means that we know that, so by Chou's theorem, it basically says that if you take two, so you start at y0, and you take another point, let's say y1, and then you know that there exists, in fact, a smooth path such that you look at this ODE, well, okay, I called it y1, but let me call it y tilde, such that y1 is equal to y tilde. So you can always, starting from y0 and y1, you can always find at least a deterministic path which, along this vector field, will go from y0 to y1. So this sort of suggests that since basically Brownian motion is going to be random enough that you can be close to any kind of this smooth path, this sort of suggests that your solution to USD it will really spread out in the whole space, so that it's really natural to hope that you have something like this, so density with respect to the Lebesgue measure. So of course this is far from a proof, and so what I will do today is show a proof of this fact. Okay, so just to conclude this presentation of the results, yeah, okay, so this is called Hermander's theorem. So it was originally proven by Hermander in, I think, 67 by analytic techniques. So because if you have Brownian motion here, you can really just see this as a PDE problem for the generator associated to this diffusion. So this is just this sum of squares operator. So basically, this is equivalent to the, okay, so in fact, Hermander's theorem in this setting is proves more because it proves that not only do you have a density, but it's smooth. But today, what I will talk about is just the existence of the density. So Hermander proved this theorem by PDE techniques, and what is really more important for us is the proof of Maliavin in the 70s, 78 also, I think, with probabilistic techniques. So what he called at the time stochastic calculus of variations, but now it's just known as Maliavin calculus. And so he just reproved this result from Hermander for Brownian motion, which was already known. But the very nice thing about this Maliavin proof is that it was very robust and could be extended in a lot of directions. And in particular, we will see today that basically a variant of his proof also works for B, which is no longer Brownian motion, but replaced by Gaussian rough path. I mean, and it was also before that extended in other directions. So, Okay, and of course, whenever you don't have Brownian motion, you cannot at all use any kind of PDE techniques. You don't have any Markovian structure. So there, these techniques would completely break down. But really, I mean, the proof that I will present today, which is the proof of this theorem when you use the Gaussian rough path, it's really very close to what would be the classical proof of Hermander's theorem by Malievin calculus, which you can find in textbooks on Malievin calculus. The difference being that instead of stochastic integral, we use rough integrals along rough paths. Okay, so this is basically what I will talk about today. But first, let me do some kind of talk about something completely different, which will be a key step in the proof of this theorem. So let me erase this here. So now let's go back to a purely rough path setting. And the first question is, I mean, what I'll talk about now is the uniqueness of the Gubinelli derivative. So let me recall some of what Peter explained yesterday or Tuesday about what are controlled paths. So we have a fixed reference rough path, which is a path plus its iterated integrals, say alpha Holder rough path. And then we define the set of paths which are controlled by this rough path, which we usually will call Y. And what that means is that essentially at small scales, Y is proportional to X in the sense that we can write the increment of Y as some function of S at, let's say, the base point S times the increment of X plus some remainder. And the remainder should be of order 2 alpha, at most 2 alpha. Okay, so this is the definition of a control path, and this is in fact the right assumptions to write something like integral of ys dxs. I mean, in fact, here I took a rough path, but it does not really matter in this thing here. You don't see the second level appear at all in the definition of the control path, but it appears here. Okay. And the question that we discussed now, so we call y prime the Gubinelli derivative. Okay, so let me be just a bit more precise now on what we really need. So y, it should be alpha Holder, and also y prime should be alpha Holder with respect to the right spaces. So, I mean, with value in the right spaces. Okay, so now what can we say about this derivative here? Is it unique? Well, of course, in general it's not. For any path, you can have, in general, you could have several different y prime. So we have a linear space. So it's just this space of control paths. Let me give it a name. I'm not sure if we will need it, but let's call it like this, dx to alpha, which basically means, I mean, this is notation inspired by Heier's notations, which means that basically y is well described by x up to order 2 alpha. Okay, so this is this space here. The space of rough path is not a linear space, but the space of path controlled by a fixed path is a linear space. And so that means that, for instance, the question of uniqueness of the derivative, it's about knowing that if you have a control path where the path is just 0, when does this imply that y prime is just the constant function 0? Okay? And if you take, and in fact, the smoother x is, and the less this is true. So for instance, if you take x smooth, well, what does it mean here? That here, let's say you take 0. What does it mean here? You have 0 y prime is, let's say, d2 alpha, that x. That means that y prime s times x st is of order 2 alpha at most. Okay? But if x is smooth, well, you could take 0 here, of course. This is true, but you could also take 1 everywhere, just because this one is of order t minus s, right? So clearly, you can take basically anything continuous that you want here, and it would work. Okay? I mean, you can really take anything that you want here. So in particular, in that case, you don't have uniqueness. I mean, this is really not surprising. And all of this is completely basic. Okay? But we sort of expect that if x, in practice, the kind of x's that we will choose will be really not smooth paths. It will be things which are really alpha holder and not better, at least not 2 alpha. And then you will have uniqueness. So there's a quite simple condition, which I can write down now. Right, so which is called true roughness. I mean, it's just a name. So we have a fixed path alpha, let's say in C alpha with values in some vector, in some bar space V. I mean, C alpha from 0t to V. And what we mean by true, okay, so at a point S, we say that X is truly rough at a point S, simply if basically along any direction it's not of order 2 alpha. So you take any, say V star, any linear form on V, and you look at the lim sup when for points which are close to V, to S, of the increments tested against this linear form. And these things here should be of order strictly smaller than 2 alpha, so you just require that this thing is equal to plus infinity. Okay? And then you say that X is truly rough if this holds on a dense set of points. And I mean, this definition is basically exactly made so that this holds, okay? And it's quite easy to prove. I will not do it. I mean, I just leave it as an exercise. Or you can look in Peter's book. Proposition. If X is truly rough, then we basically have this thing here. So 0 y prime. If you have, yeah, you have uniqueness of the derivative. So any control path, or maybe okay. Maybe let's just okay. Let's keep it like this. This implies that y prime is equal to 0. Okay, I mean, this is quite easy to see with this thing here, right? So basically, you just write this condition, and clearly, I mean, this thing will blow up, will grow strictly faster than this one in any direction. So the only way to have equality here is if this thing here is 0. I mean, it's just a few lines of proof. And in fact, the thing that we are more interested in, the form of this uniqueness of the derivative that we will use, is that in particular, as a particular case of this, you can write that if some integral against x is equal to 0, this implies, so here let's say that y is a control path, so that you can really define this, okay? Then this implies the only way to have a 0 integral by integrating against x is to have a 0 integrand, okay? So it's a purely deterministic statement. It's somewhat reminiscent, or I mean, in probability theory, there is also this kind of statement for, okay, so first, this also holds if you add to this something which is smooth, or let's say some drift. So also if you have integral of z dt plus integral of y dx is equal to 0, this implies basically that all of this are equal to 0. Yeah. So we will really see this. This will in fact be exactly the last step in the proof of the theorem to use this condition. And there are some probabilistic statements which are similar, which is, let's say, the uniqueness of the Dubh-Meyer decomposition. But this one is really a statement about martingales, and here we don't have any kind of martingales because, okay, this would not really work with fractional Brownian motion, for instance. Dubh-Meyer decomposition. Okay. We have really something which is purely deterministic and, in fact, very simple. I mean, all this is quite elementary. Right. Okay. All right. So, are there any questions up to this point? So, then let me continue. So, keep this in mind for the remainder of the lecture. Okay. So now let me go more clearly into the direction of what we need for the proof of the theorem. And let me talk a bit about Malevin calculus. Okay, so what is the idea of Malevin calculus? Let's see. Okay, so what we're studying here is we have the map which to a path maps the solution to a differential equation, okay? So we look at the map which to x maps to y, solution of the differential equation. As we've seen, if we look at basically any Banach space on which we could define x, I mean, or as has been explained, this map is never, you can never find it, you can never find a Banach space which is rich enough to contain Brownian motion to have this to be a continuous map, okay? And this is the whole point of rough path theory. Spaces such that, okay, let's call this map pi, such that pi is continuous and which are rich enough to contain, let's say, sample path, for instance, of Brownian motion, or let's say also fractional Brownian motion, so all kind of stochastic processes, okay? So and these spaces, the spaces of rough paths are not linear. It's not linear space. So this map here, let's say if you look at it from the space of continuous functions to space of, just to R, if you just look at yt, a fixed time, this map, it's not continuous. But what Manifolds calculus does is, so you have to assume more structures. You have to have a Gaussian structure. A Gaussian, it's closely associated to a Gaussian measure. And it's, what Manifolds calculus does is tell you that this map, which is not really continuous in this general sense, but it will be, in fact, smooth if you strongly restrict the tangent directions in which you're allowed to go. Okay? It's going to be smooth along certain directions, which are the Cameron-Martin directions. So I will explain this a bit. And you need some structure. So for instance, it's not going to be smooth everywhere, but only on set of full measures, etc. OK, so let me explain a bit more. So in any case, I will definitely not go into any details on Manifolds calculus today. And in fact, we will really use a result on some sufficient criterion given by Manifolds calculus to have existence of a density. But I will not prove this result at all. So it will be just some kind of black box that we use to be able in the end to have our theorem. But I will really not go into the proof, anything deep about Manifolds calculus at all. OK? So we have our sample space, omega, which here we can just take a continuous function from 0t to Rd. And on this space, we have a Gaussian measure. Let's call it P, probability measure. And by Gaussian measure, I mean that just basically, if you take any finite number of coordinates, this will be a Gaussian measure. So e.g., say if you take any finite number of times, xtn, with, OK, you look at their coordinates. Well, it's not so important. In, this one is Gaussian random vector. So it has a Gaussian law in Rn. And now, so let me define what is this Cameron-Martin space along which we're going to translate things. So I will give the definition of the Cameron-Martin space, but it's not so important. But just, let's say, for sort of completeness, OK? So let's call it H, the Cameron-Martin space. It's a subspace of our continuous functions here. And it's given by the function small h. OK, let's miss. For each time, we have the expectation of some random variable z times our vector, xt. OK, xt is our random, is given by our random measure. Okay, so here this is the expectation with respect to this measure. And you don't take any possible random variable, of course, where z is basically a linear function of, almost a linear function of our Gaussian vector. Okay, so z is, in fact, in the L2 closure of the span of these coordinates. Okay. Right. So this space is also just, so that you know, is also called the first Wiener chaos. So you take a linear combination of Gaussian random variables. So what you get is just, so this is just a scalar valued random variable, and it's a Gaussian random variable. Okay. And then when you take the expectation against the random process, you obtain your Cameron-Martin function. And so H on H, you can define a Hilbert space structure simply with the scalar product associated in L2 to these random variables. So H prime in H, this is just defined as just the expectation of the product between Z and Z prime. And okay, so what would be the most important property of this Kalman-Martin space? So I gave the definition, but like I said, it's not so important. The most important, the most fundamental property of this Kalman-Martin space is that when you translate along a Kalman-Martin direction, and you look at the measure that you obtained, and it's equivalent to the first one, to the original measure. So let's say you define TH from omega to omega just as the translation. So you add this Kalman-Martin direction. Then, if you look at the measure obtained by, let's say, after this transformation, this is equivalent to P, meaning that sets of zero measure for one are also sets of measure for the world. And this is an if only if H, so here H can be any element of the sample path, of the sample space. And this is, you get an equivalent measure if and only if you have translated against an element of the Kalman-Martin space. So it sort of suggests that if you want to look at translations of your path along some direction, then this is going to be the right object. And for instance, what you can see is, I mean, typically, if you look at any neighborhood of the constant path, if you look at any neighborhood of the constant path, it will have positive measure for your Gaussian measure P here. And this directly means that any element of the Kalman-Martin space, any neighborhood of this path is going to also to have positive measure. So you really have path close basically to any element of the Kalman-Martin space. And in fact, so this space here, H, I mean, in general, I mean, at least as soon as you have really a infinite dimensional thing, it's going to have zero measure. So this path here in general much smoother than the random path that you get. But any neighborhood of this Kalman-Martin space, for instance, is going to have full measure. Okay. All right, and okay, and just this thing here is also important. If, for instance, let's say you have an element big F in L2 of omega with respect to this measure here. Okay, so L2, it's not really. So you have F, let's say, which from omega F of omega in R, but elements of L2 are only defined as equivalence class of functions, right, up to P null sets. So if, in general, if you just have, here I take L2, but it doesn't matter that the 2 here does not matter, okay? Just a random variable which is defined up to P null sets. And then what happens if you want to look at the map which look at the translation, okay, F of omega plus H. Then if you look at any directions, this would not even be well defined in general as operating on this spaces of random variables, just because, right, so if you have two, let's say, elements which agree up to P null sets, that definitely does not mean that for an arbitrary translation, this will also hold, okay? But because of this statement here, if you take Kalman-Martin direction, this holds. So this sort of suggests that this is really the right direction along which you want to look at translations and operate as with translations on these random variables. All right, so now let's just not talk about this. We don't care so much anyway, because we don't have really this kind of problem when we use rough paths. Okay, now let me give the kind of differentiability that we will use. So Malevin calculus, usually you can have some kind of weak derivatives along this, in this direction, some kind of Sobolev definitions, but here in this setting we have something which is rather strong, so let's call H differentiability. And we have a function f, so now it's really a function, say from omega to, let's say, r. And say that it's h differentiable, which we call C1h, if for all almost on a set of full measures, so for p almost every omega, then you look at the map, basically translating omega along the Kalman-Martin directions. Then the map h maps to f of omega plus h, so defined on the Kalman-Martin space. And what we ask here is that this map, so of this translates along this Kalman direction, is differentiable, so Fréchet differentiable. And as we will see, for instance, this will hold for our differential equations, the solution map to our differential equations. And so let me conclude this first part with, so then when you have this Malevin calculus, you have some integration by parts formula, and there are some criteria which tell you that, so when does this kind of random variable here have a density with respect to Lebesgue measure? And so us, we don't have some, we are valued in some e-dimensional space. Okay, and the criterion that we use is due to Boulot and Hirsch. And like I said, I will definitely not get into the proof of that at all. Oops. So let's say we have this time f from omega to Re, and f is in C1h. Then if, and then you look at the covariance matrix, so-called covariance matrix. So it's just, okay, f is some vector, f1, f2, fe. And so you have the differential derivative in f, h of f I. Okay, so this one here so it's a derivative on this space H, so it's basically, again, an element of H, right? And so you can pair it with another one. So this thing is defined at least out of a set of measure 0. And what you ask is that this matrix here, so this E times E matrix, has to be invertible. So this is, right, okay. This is an element of, this depends, of course, on omega, so on this function of omega, which you look at the different derivatives at 0. And you ask that this matrix here should be invertible for P almost every omega. And then the statement is that under this criterion, then F admits a density with respect to Lebesgue measure on Re. Okay, so basically this says that for every path, you can always, just by changing your path a little along some Kalman-Martin directions, you can always go also in all directions, right? Which suggests that you should have a nice density, or a density. And this is exactly the statement that we will use in proving that our solution to our differential equation has a density. And I think we can take a short break now, so maybe 5 minutes, and then when we come back, or maybe even 5 or 10 minutes, I think I should have enough time. And when we come back, I will explain the assumptions on our driving signal and give the proof of the theorem. Okay.
non, c'était Peter.
Ouais.
Je connais la version.
Ah ouais, c'est une vieille version.
D'accord, donc c'est pas les livres. La true roughness dont tu parlais, moi c'est ce que je retrouve ici.
Ouais, ça c'est. Non, ça c'est pas ça en fait. Ça c'est la version quantitative. Donc c'est plus compliqué, mais si tu veux juste l'unicité, t'as pas besoin de ça, mais il faut que tu prennes la version plus récente.
D'accord.
C'est dans la version récente en tout cas du livre. Il est disponible sur la page de Martin Eyrer.
Oui, j'ai vu que c'est.
Donc,
d'accord.
parce que ça, en gros, c'est. Si tu veux prouver l'existence d'une densité, tu dois avoir des. Non, la régularité de la densité, tu dois estimer les moments de ton déterminant, ou l'inverse du déterminant de ta matrice. Et pour ça, tu as besoin de trucs quantitatifs de ce genre-là. Mais si tu veux juste l'existence de densité, tu as juste besoin de
l'inversibilité.
Voilà, et donc pour ça, tu as juste besoin de savoir, en gros, c'est juste une récurrence où tu as, je sais pas, comme la preuve classique, quoi, intégrale de quelque chose d b égale 0, donc ce truc-là égale 0. Oui. Donc ensuite, tu le réécris encore comme une intégrale, etc. Voilà, mais donc oui, la true roughness, c'est aussi dans la dernière version. Et de toute façon, ce que je fais aujourd'hui, c'est aussi en entier dans le livre de Peter.
D'accord, ok.
Le chapitre 11, tu vois, il y a... Non, attends, voilà, chapitre 11, section 3, Manifolds calculus.
D'accord.
Thanks. Yeah. I don't know, I do things differently from Peter, who will always, be talking about things in sort of a vague way, and I usually, I don't know, when I prepare something, it's easier for me to just do things in a very linear way. And,
for me, it's sort of, it's good when things are in detail, because then otherwise you start thinking about how you would fit in the details and then you get lost in that stuff and you can't follow anymore. I prefer it this way. So is there for the true roughness thing, is there a converse to that as well? So say, for example, if you replace that 2 alpha in the denominator by like anything less than 2 alpha, would you always be able to find a counterexample like in the smooth case?
Well, I mean, yeah, that's different. I mean, I mean, the smooth case, it's not really smooth, it's just 2 alpha also works, basically, right? As soon as you have 2 alphas, then it's enough.
It's enough,
So, I mean, then, I don't know if you want to do something which is maybe something like, if you look at the fixed points, at least it is, and if you want to do something like, okay, there is no dense set of points such that you have this condition, then, okay, if you're trying to find it can get messy.
A little bit messy, but I'm just thinking like, assume that it holds for all points or something, or I've never taken like a course or ever read properly everything about modular calculus. All my knowledge of it is like from bits and pieces here.
Yeah, I'm not such an expert myself.
Fine, you?
Yeah, I'm bad. Good. Yeah, I managed to catch the lady
upstairs. Oh yeah, she
was there. Yeah.
Okay, so you're fine with your registration and stuff,
and stuff.
Registration and
reimbursement. Paperwork and everything. So it's all sorted. Yeah, I think she may still be there later today. Actually, if you were trying to catch her.
I need to catch her.
Peter had also written some lecture notes on Manifolds calculus, right?
Yeah.
A long time ago.
Maybe there's somewhere on his webpage or something.
It's a part of the material.
It's actually also part on paper by, not on paper, but I guess more notes by Martin.
Right, this on the yeah, definitely that was an inspiration.
here for this true roughness notion?
No, it's in
It's not
section
this
6.
chapter, okay.
Yeah.
Okay, good. Homework for me.
Yeah.
Thank you.
Definitely, you're picking up more rough paths. You're picking up more rough paths then.
I think, I believe.
Yeah.
I hope.
I hope I have this well, actually. I hope I have this well. It's always a learning curve. Like, no matter like, if you keep on going to rough path sessions, you always see something new all the time, at least for me.
Yeah, even if you know much more than me, yeah.
I wouldn't be so confident of that.
No, I am. You can be not confident, I am confident. But yeah, what happens is that there's a very productive community, right, working on this topic. So it's the fact of seeing all the time something new, right?
Oui, s'il vous plaît, merci.
I mean, also some of the articles that the Peter lecture notes rely on are very recent ones, right? Some stuff
Definitely.
from the.
I mean, this stuff is quite recent. Even this is.
2010 or something. So, well, of course, well, no, the campus is old.
Yes, but this results.
Specific applications.
Yeah.
Actually, just do you know if there's a coffee available?
Not during this break, I believe.
No, it's
before the lecture, yes. There was a lecture. There is a lecture at 9, right, from 9 to 11, and then this one. And in between the two, there should be a coffee break.
I guess, I'm not sure.
But I believe if you go to the second floor, you could always find something. If you want, that's what I'm doing, by the way.
Okay, We'll be back in like 2 minutes.
Sure.
Faire la régularité de la densité alors.
Non.
C'est fait dans leur livre ou pas?
Non,
ils font juste l'existence.
Ouais. Parce que l'existence, c'est vraiment c'est 2 pages de preuve, c'est assez facile. Voilà, c'est ça. Mais par contre, il y a quand même dans leur livre ce genre d'estimés quantitatives.
Ils les donnent un peu quand même.
Ouais. Mais ils font pas du tout l'application au calcul de Maillard.
D'accord. Ouais, parce que ça, c'était un autre tour de force de Martin, c'est
ouais.
estimé, tu sais, le même de Norris.
Ouais. Toi, tu as fait quelque chose avec lui là-dessus, avec le nouveau FBM.
Fractionnaire, donc un H supérieur.
Ouais, d'accord.
C'est assez impressionnant ce que c'est généralisé dans le cas
ouais.
des estimés quantitatifs.
Ouais, c'est vrai que c'est pas... Mais donc non, je vais pas du tout. Enfin, j'en parlerai peut-être très rapidement à la fin, en passant, en expliquant. Start? Okay. Okay, so now let me explain the setting in which we're going to fix ourselves. So we still have this Gaussian measure, right? So x of omega. So still as before, right? Gaussian process. And we deal with rough paths, so we assume that it lifts. Let's assume that X has a natural lift as a rough path. As alpha rough path, okay? And still alpha between 1/3 and 1/2 to be in this level 2 setting. So what I mean here by natural lift, maybe Peter explained this quickly Tuesday, I'm not sure, but so at least for P almost every omega, well, so X of omega, so I mean this is just in fact omega, is alpha Holder continuous. And then you can define a second level, X of omega, which is just obtained as, let's say, the limit of discrete integration, say, so integration over partitions Pm with steps which go to 0, but it's just P, X tensor dx. So this is just Riemann sums, right? So this thing exists almost surely, so for every omega, and it satisfies the correct 2 alpha norms. Okay, so this is just what I mean by X has natural lift as a rough path. And there are some conditions to make sure that this happens. So true under some conditions on the covariance of X, right? And so X is still a path. So we are still in this setting where we have something from 0t to Rd, so it's d-dimensional path, true under some condition. And in particular, I mean, it holds if you take d-dimensional Brownian motion. For d-dimensional Brownian motion, and also for fractional Brownian motion with first index greater than 1/3. Okay. So this is the basic setting in which we put ourselves. Now, okay, so now what we want to do is, what we look at is the map. Okay, so we have the map, and okay, now we have y, just y, the solution to the rough differential equation, dyt equal to so what I had in the very beginning, so vi of yt dxt. X, of course, this is a random variable again, something which depends on omega, but I will just not mention this anymore. Okay, so and we can call, and this is in fact, so I don't know how we can call this, but okay, so this is, okay, let's say some function of, so y, so y times t, because that's what we are interested in. It's some function of, the rough path times omega, so yt of omega. And so now what we want to look at is the translations of this variable against the Cameron-Martin directions. So we know how to define, so this map F here is just the solution map, right, which to a rough path associates y. And as we've seen before, this is a very nice map, it's continuous and so on. So the only thing that we need to do is be able to define the translated rough path, okay? So we want to have x bar of omega plus h. So I mean, this is this x bar, it's two levels, so the path and the area. So of course the path, this thing here, the path is just, so you have x of omega and you add the path h, okay, this is continuous path. Right, so yeah, okay, so I will just explain a bit. And then you need to know the iterative integral. So you want something which should be something like x plus h tensor d of x plus h. So this is just quotation because it does not exist in classical sense. So this, what does it mean? So you just, okay, so let's say, let's just focus now on the second level. What it should be equal to is something like this. So you just expand this thing. So you have x tensor dx. So this thing you already know what it is, right? Just by definition of the rough path. Just x of omega. And then you have remaining terms. So you have integral of x tensor dh, integral of h tensor dx, and integral of h tensor dh. So typically, H is going to be smooth enough that this is always well defined. Another question is, how do you define this? And basically, we will just make the assumption that ensures that these things are defined as classical Young integrals. Okay, so assumptions. I will have three assumptions. So let me call this one A1, which is known as complementary Young regularity. Okay, so I need to make a small thing here is that, in fact, Holder spaces are not the right thing to look at now. And just, let's say, p-variation path. So the p-variation path with finite p-variation, this just means that, let's say, the p-variation norm of x is just the supremum of the increments of x over p. Okay? Sum over, let's say, some partition. Let's say sub of p. Let's say si plus 1. And so it's easy to see that if you have a alpha Holder path, it has finite 1 over alpha variation. And in the other direction, so it's not true that p variation implies Holder regularity, but it's true at least up to reparametrization. Okay? And so so in the original Lyons articles, everything is done with p variation. Rough paths work basically with p variation as well as with Holder spaces. It's just maybe a bit simpler to state things in Holder spaces. In general, when you just deal with the stochastic process, you can just use alpha Holder spaces and not p variation, just because Brownian motion or basically many stochastic processes, for instance, they have basically the same regularity in every interval. So you don't need really. So yeah, there is this homogeneity. But whenever you're going to look at deterministic things, so for instance here, Cameron-Martin spaces. Okay, so I see that I forgot something before. Okay, I will just go back. But here, for instance, Cameron-Martin elements, they in general, they don't have to be the same around every point. So they can have, in general, they have better p-variation regularity than alpha Holder regularity. Okay. Yes, yes, X is the coordinate process, yes. Okay, and maybe Peter talked about this, but when you have f and g and you're trying to define integral f dg, say 0, 1, okay. If you have Holder coefficients which add up to something which is strictly greater than 1, then this works, and then this is okay. And also, if you have for p variation, you have basically the same condition. And this thing is well defined and continuous as soon as you have this Young condition, which is that the inverse of the coefficient add up to something which is strictly greater than 1. Okay, and this is known as Young integral. Okay, so here we basically just assume that we can define these things as Young integral. Okay. So our assumption. So okay, so this was just parenthesis, but the real assumption is H, the Cameron-Martin space, is continuously embedded into paths of Q variation with 1 over P plus 1 over Q strictly greater than 1. And here, 1 over P, I mean, this is, you can say alpha if you want. But, right. But okay, so one thing why it's not so, in fact, we have to work with p-variation paths is that this thing here, of course, it does not stay in the Holder spaces, right? Just because this thing here, it has finite variation, but Q variation, but it's not Holder in general. So this thing here will have the right variation, but not. Okay, so something which I forgot to say earlier is just to give an example of Cameron-Martin space, which I mean, sorry, is helpful. So let me now give it now. Okay, so for Brownian motion, and the Cameron-Martin space for Brownian motion is just this h such that they have a derivative, so they're absolutely continuous. And in fact, their derivative has to be square integrable. Okay? Let's say what? Let's say dt h dot squared strictly smaller than plus infinity. Okay? So then if you come back to the definition, we had this random variable z, and here it's just going to be this winner integral of h dot s dws. And you see, for instance, and then the scalar product on h is just a scalar product in R2 for this derivative. Okay. So, for instance, what happened in this case? Then, right. So this is just, let's call it, I don't know, just Sobolev space, right, of functions which are. Okay, so of course have h of 0 is equal to 0. Sobolev space of order 1 and L2, basically. So now, h, so you have this L2 norm for the derivative. So in particular, the derivative is in L1, right? So that means that you can really bound the one variation, which is quite strong. But if you were trying to, look at Holder continuity, then you'd all that you get is 1/2. Okay, these functions, when you measure in Holder, it's definitely much worse than when you measure in variation. Okay, because for instance, 1/2, if you're trying to look at the integral of any 1/2 Holder continuous functions against Brownian motion, then it's not enough because Brownian motion it's 1/2 minus epsilon, so you get something which is definitely not greater than 1. Okay, but however, here, for instance, so as an example, here for Brownian motion, this condition holds just because we have q is equal to 1, in fact, so just having any p here would be enough. But so Brownian motion satisfies this condition. You can again write some conditions on the covariant functions such that this holds, and this is basically true for fractional Brownian motion, even up to order 1/4. So all the fractional Brownian motions that we can lift as rough paths. And of course, many more, I mean, there are a lot of more processes, but I mean, let's say at least the example that we want to be able to extend the Hofmann's theorem to would be the fractional motion, and this holds for this. Okay. All right. Let me see if I forget something. Okay, yeah, just quickly. So once you have this, you can just define this translation here. So then you have, for any rough path x bar, you have this translation th of x bar. So here, which is a p variation rough path, you can define th of x bar basically exactly by these formulas here, right? For h in q bar. And then you can basically prove that, I mean, there is this lemma which always appears, that if you look at x bar of omega plus h, I mean, this is a well-defined random variable, right? You have this omega plus h element of your sample space, and to that you know that for almost all of those you can associate the rough path, and I mean, it's quite easy to see that this will coincide with this function here. And the real result is for almost every omega, this really holds for all h. I mean, which is quite strong. I mean, okay, as seen here, it's not trivial, right? You have to, there is something to prove, but it's easy to see once you know that all of those will coincide with this object, basically. Just for outside of the null sets, you can write this as the limit of Riemann sums. So this means that now when we're looking at this Malievin differentiability, we're just trying to look at f of th of x bar minus f of x bar. Okay. And in fact, the omega, we don't care so much about the specific probability here anymore. we'll just, basically for any rough path here and any path h of Q variation, you will be able to define this. Okay, so this is the first assumption. Now we need two more assumptions. So the first one, so the first one is a local assumption on the path of x, which we've already seen. We assume that it's truly rough. Okay, so that at small scales, it has enough oscillations. So A2, which is just, again, P almost every omega. X of omega is, let's say, P or alpha, truly rough. So this will really appear very naturally that we need this assumption in the proof. And finally, so this was a local assumption on the path. And we need now a global assumption, which is the following. Let's say, which means that basically the Kalman-Martin space is big enough that let's take F in C P var valued in RD, such that for all H in H in the Kalman-Martin space, so which we can decompose in D coordinates. And if you assume that basically this integral of Fi dH I, well, okay, is equal to 0 for, if this integral of F against H is equal to 0 on each, for each element of the Kalman-Martin space, this is only true if F is equal to 0. So this is more a global assumption. And so, for instance, one example of a process which would satisfy the first two assumptions but not this one would be a Brennan bridge, right? So Brennan bridge is basically a Brennan motion conditioned to come back to its starting point. And then, obviously, this is not going to, the Homander theorem is not going to hold for this one, because then you can take yt just equal to dxt, and then clearly, I mean, at times t, you're always back at 0, so you don't have a density. Okay, so you would need some kind of global assumptions to ensure that this does not happen. And again, you can prove that this thing it holds for fractional Brennan motion and for Brennan motion, for fractional Brennan motion. You can also do not exactly a Brennan bridge, but let's say, I mean, one of the examples that they gave in their paper was a bridge which returns after times t. So let's say bridge at such that x, let's say, time t plus epsilon equal to 0. So this kind of thing which would also work. Okay. And yeah, and basically these assumptions are what you need to have the Homander theorem. So let me write the theorem, and then I will give the proof with that. Now that we have everything in place, it really follows quite nicely. I mean, it's just a matter of writing some notations and making sure you don't mess up indices, but Okay, so here's the statement of the theorem. So let X satisfy all these assumptions, basically A1 up to A3. And then we assume the Home-under condition also. Let V1, Vd, again, smooth vector fields, such that the Lie algebra at the starting point spans the whole tangent space. Then, I mean, the statement is just exactly the same as before. Then, okay, and we'll also write dyt. Okay, I didn't have this here. It's driven by X along the vector field Vi. And then, conclusion, then for any fixed T, okay, let me just, okay, then, right, so here I have a fixed T, so then Yt has a density with respect to the Lebesgue measure on Re. Okay, and now I will just give the proof. So of course, what we want to do is use this Boole-Hirsch criterion. So we're going to need to look at what is the derivative of this functional here in the Kalman-Martin direction and so on. So I need to introduce some notations now. So let me make sure I get the right thing. Okay, so first let's call U the solution map. Okay, U from 0 to T of Y solution map. So this is the solution to this thing here. Yes, and what we emphasize here is the dependence on the starting point. So again, here this is for a fixed rough path. Okay. And here I write 0 to T, but you could have any from S to T also. You could also have for S, I mean, yeah, it doesn't matter that S is smaller than T. You can also reverse time and so on. So it's not a problem. And then what we're looking at, we're going to need to look at the derivative of this. So the Jacobian, G from 0 to T, this is the derivative of U of X bar. Okay, and the important thing is that, so for now, let's assume everything is smooth, okay? Let's assume that just X is a small path, so that this is just a classical differential equation. Then you can write also a differential equation for this one here, which is just obtained by formally differentiate here. So what do we have? dj from 0 to T, so this is a differential in T, right? And you just differentiate this formally, so you get sum from I equal 1 to D of dVi of Yt. Then you have the so chain rule, right? You differentiate I, then you differentiate Y. Right, and the derivative of Y is exactly J. This is Y. J 0 times dx. So you have a linear differential equation for J, which is this one. So yeah, I'm just taking this to make sure I don't mess up the notations. Okay. And then, right, the formula that we're going to use, what we're going to need is more precisely than this. What we need is this J. So first, instead of going from 0 to T, we want to go from T to 0. This is just the inverse, right? This matrix J, just because we have this flow property for this, we have also this property, this multiplicative property for J. That and this just chain rule applied to this thing here. And so now what we're going to need in the end is this thing from T to 0. So this is a matrix applied to the vector W at the point yt. And we want to know what is the differential equation satisfied by this, okay? And this is exactly where the Lie brackets are going to appear. So maybe, yeah, I'll just write down the result. But it's just, you can just basically use the chain rule. So you have to differentiate this, and you will see that basically, okay, so just from this, you see clearly that at some point you will have the derivative of the VI's against the vector field W, and when you differentiate this, you will have the derivative of W against the direction into which Y moves, which are exactly the VI. So I mean, it's just quick computation. You will see that you will have appearing the Lie bracket between W and this vector field. And the exact formula is this thing here. You have sum over I, again, J 0, T to 0 of the Lie bracket at yt dxt. So this thing, okay, maybe we will definitely need to use this one. So this is just the derivative of the flow. Now what we want to do is perturb the driving signal x, okay? So dh x. Okay, so now what we want, yeah, dh. So what we want to be able to have is the derivative. I'm not sure what would be the correct notation here. Right. Okay. So, yes. So derivative in this of yt in the direction of a direction x. This means basically should be equal to the limit of. I mean, just a derivative, just, okay, I'm not writing it down. This is just a directional derivative when you replace your path x by x plus h. And so what happens? So let me write down again, this is going to be given by an integral from 0 to t. So what happens is that basically, right, so at each time t, you add some bump you have in these directions, which will mean that your y will be perturbed. You will have some of these things added here. So let's see. When you have hi, this will add hi times the I of ys to the path, basically. And then this is going to be seen in the terminal time just by exactly this derivative of these things between the time s at which you're doing the perturbation until the last time. Okay, so j. So this should be the right thing. So let me just check that I did not mess it up, but yeah, okay. And of course, it should be you have this sum again from 1 to t. Okay, so this is some notations. So for smooth path, this is completely standard. I mean, you can do it directly. And the point is that this also holds whenever you take a rough path. Okay? And here, then h should be any element in Q variation. Okay, so for instance, so now these are going to be rough integrals. Rough integral. So here, for instance, what happens is that, well, you have to make sure that here, this thing here is controlled by x, but here y is a solution to an RDE, to this differential equation, so it's already controlled by x. Then this means that this thing here is the solution, again, of a differential equation driven by x. So everything is really a controlled path here. And this one here is just simply a Young integral, right? Because here you have something which is basically of the same regularity as x, because you have things which are controlled by x, against something of Q variation, so it's just a Young integral. And with continuity of the Young integral, you can check that these formulas which are for the Young integral and rough path, you have to check that these formulas which are true for smooth path will also be true for when you have rough path. Right, so, and then you need to prove that this is really something which satisfies this C1H condition, that it's Frechet differentiable. but yeah, it's not hard to prove once you have this formula. And now, okay, now we can basically finish. So we have this, and now what we want to look at is the covariance matrix, right? So let me call it MT, the covariance matrix. So let me recall what it was. It was dH of yt, let's say all the components, I, j. So this E times E matrix. And what we want to know is that almost surely it's invertible. So now we just fix, we really are going to work pathwise. So we fix omega, we fix our rough path that we get, and we want to know that this thing is differentiable. So let's fix, so for that we just have to take a vector z in Re, and we look at z. So we have this symmetric positive matrix, so it's basically, it's invertible if and only if this is only true for the zero vector, right? So what we want to, so we're going to postulate this, and we want to know, does this imply that z is equal to 0? Okay. And then what we're just going to do is write this in terms of a rough integral, and then by some induction procedure, we'll see that z is orthogonal to all the Lie brackets of the vector fields at the starting points, and this will imply by assumption that z is equal to 0. Okay, so let me write, okay, so what does this mean? Okay, so this is, you can write this as sum. In fact, just with this form here, you see that you can write this as sum for I equal 1 to D of so Z against dH of Y T I squared. So, I mean, the notation is maybe a bit messy. So here we have something in Re. Wait, so no, that's not right. Wait, what is it? No, okay. No, that's not correct. Let me. Okay, I need to take the notes, I'm not sure. Right, okay, so okay, let me try to write it, but so what we should get in the end, okay, maybe I'll skip the computation because right now I'm just a bit confused, but what you should get is a sum from I equal 1 to D, right, of, it should be the same to say that if you look at this MT, which is obtained as the element of the Kalman-Martin space, which satisfies this. So wait, there's something wrong here. No, okay, wait, definitely something wrong here. No, okay. Okay, so what you should obtain is that for all elements of the Kalman-Martin space, so which is H1 to HD, you have basically that this integral will vanish. Z scalar integral from 0 to t So if you do the computation correctly, this is what you should obtain. Okay. And just by writing this, okay, you have to, so this is a scalar product in H. I mean, now I can't do it off the top of my head, but it's just a matter of writing things correctly, keeping in mind the right dimension and so on, and it's really something like this, okay? And so what that means, okay, so the first thing to simplify, okay, we will want to use this formula here. And for that, it's better if we don't have from S to T, but from S to 0. But, I mean, this is just, you just replace Z by Z times J from 0 to T, right? So this, you know that it's always an invertible matrix, so you can just do that without a problem. This does not change this condition here. And so you have this. Okay. And so now, well, I mean, now you see quite clearly what you have to do. What do you do? Well, you use this A3 condition here, okay? Because here you have some function of S, which is this Z scalar, this thing here, which vanishes against any element of the Kalman-Martin space. So by A3, this implies that for all I, this integrand vanishes. So Z scalar J 0S Vi of Ys is equal to 0 for all S in 0T. Okay? So first thing that you do is, in particular, you look at time 0, right? Time 0, this is just the identity from 0 to 0 of Vi of Y0, Z scalar Vi of Y0 equals 0, again for all I. And then, I mean, now we basically finished. And then what you do is you use this formula, okay? Since you can write this as an integral again, so this means, okay, let's just write it directly here. That means that integral for any t, integral from 0 to t of Z scalar J0S of, so here what happens is, so you use the formula for this thing here where W is equal to Vi, okay? So again, for all I, if you look at the sum over J of Vi Vj at Ys dxs is equal to 0, so equal to 0 for all t. So what does that mean? Well, then that means that then what you use is exactly this, what I talked about in the beginning, this true roughness, that the only way this rough integral is 0 is if the integrand is 0. So here I just have to make sure I have the right indices, okay? So that means that for all I and for all j, Z scalar J0 to S of Vi Vj of Ys is equal to 0. Again, I mean, then basically you're finished, right? You just do the same thing. In particular, if you take at time 0, Z is orthogonal to all the firstly brackets Vi Vj. And then by induction, you just do the same thing over and over again. And by induction, Z is orthogonal to the Lie algebra generated by vector fields at time 0. Hence, Z is equal to 0. Hence, I mean, this matrix is invertible, almost surely. And you have this Bühler-Hirsch criterion. And in conclusion, your random variable yt has a density with respect to Lebesgue measure. So that's it for the proof. Okay, so, right. So I'm finished now. I will just give a few references where you can look this stuff up. So the presentation that I have followed today is the presentation in the book of Peter Fritz and Martin Heirer. They have a recent book on rough pass, and there is a chapter on this kind of thing. So it's well, they basically have this exact proof. So Fritz, Heirer. So it's a book which is called Course on Rough Pass. So you can buy it, or if you want maybe easy to get it in an easier way, it's available for free as a PDF on Martin Heirer's website. Okay, so this is the presentation which I have followed, which is a simplest presentation, I would say. Then originally, this theorem which I have presented today is due to Thomas Cass and Peter Fritz in a paper, I think, around 2010, which was in Annals of Math. And so it's, yeah, the assumptions were a bit more complicated. The proof was also maybe a bit more complicated, but they simplified it later. So this is for the existence of the density. And then if you're trying to go further and trying to prove that you have a smooth density, you can also do it, actually. And maybe slightly stronger assumption. So basically, again, Malevin calculus gives you some criteria under which you have existence of a smooth density. And it's just that instead of knowing that your matrix, covariance matrix is invertible, you have to have the stronger statement that the inverse determinant has moments of all order, basically. And to do this, okay, so the main point that you have to do is to look at a quantitative version of this true roughness thing. So true roughness is just if this integral against dx is equal to 0, then the integral is 0. And you need to have some statements of the form, if this integral is small, then the integral is small in some sense. Okay. And so now let me give the reference. So this is done in a paper by a few people. So again, Thomas Cass, Martin Heirer. So I just need to have the right alphabetical order. Okay, so then Christian Litterer and Sami Tyndall. And this is, I think, 2012. And yeah, so that's it. Thanks. Sorry? Oh, yes, yes. So tomorrow I will talk about the work of Martin Heirer on regulatory structures and how to, so basically the point is to do for PDEs what we can do for ODEs with rough pass.